Okay, I think we'll get started. People outside, if you can hear, if you want to come in. Oh, they're moving. That's cool. there's a gaggle of them. So we have Matthew from Matrix. He's talking about low bandwidth, as he put it, on crappy networks. So we know all about those.
Yep, pretty much. So hello everybody, can you hear me all right? Is the microphone working? Good, perfect, brilliant. Come in, don't be shy. Come and find all about what we're doing with low bandwidth matrix stuff. I guarantee it is the only low bandwidth talk in this conference, I think. So if you want to hear what we've been doing, now is a great time. First of all, matrix, I'm guessing most people probably know what it is already. Anybody not confident? Okay, we've got one person, a little bit. I'll do a quick recap anyway. So Matrix is a new protocol and a new network for secure decentralized communication. And we're targeting the use cases of interoperable chat, VoIP, any kind of real-time data synchronization, to be honest. Could be for VR, AR, mixed reality, could even be for IoT data synchronization. And the point here is to create a global decentralized end-to-end encrypted communications network, really the kind of missing real-time component of the web. Obviously, the web was meant to be real-time. It was meant to be read-write in the beginning, and for many reasons, it ended up being this very sort of write once, read many times kind of idiom, where if you want to publish something on the web today, even now, you have a choice between using some random web app like WordPress, or you could FTP it somewhere. You could use DAV, possibly, if it's like the mid-90s. And there's no consistent way to really publish data there at all. So we want to provide APIs layered on top of the web for distributing JSON in real time and receiving it too. So practically speaking, one of the things we can do is to build up a network that connects together the communication silos of today. So this could be something like Slack, it could be Discord, Telegram, it could be the old IRC networks, it could be something like Gitter, or it could be another standards-based solution like XMPP, it could be SIP and Simple, it could be really, well, we've got 60 or 70 different bridges now to different networks for different things. We even have WeChat as of a few weeks ago, and for Chinese users, there are bridges to Skype, Skype for Business, Same Time, if anybody's using later Same Time. It's really amazing in some ways because Matrix is a completely open project and it's very easy to write these bridges. People pop up and go and implement for whatever platform they like. And Matrix itself sits in the middle as the kind of highest common denominator protocol to try to link them together. So in practice, you get servers like these guys, the big blue dots. You have native Matrix clients, the green dots, and then you have light blue dots, and these are application services, typically used as bridges, but they are basically clients, like the green ones, but on steroids. They can go and replicate users on other protocols. So for instance, the Telegram bridge here can act on behalf of all of the users on Telegram who want to interact with Matrix and go and kind of masquerade them into the wider Matrix network. So there are lots of rooms of Matrix which have users on it via Slack or via IRC. Quite a common combination is IRC and Slack. Imagine you're an open source project. You start off on Freenode. You then have people doing a bridge to, say, Discord and Slack, and your community is splintered. Some people like Discord, some people like IRC, some people want to use Slack. Matrix provides a way to glue it all together. Obviously, you don't need to use the bridges, and honestly, in some ways, the bridges always suck. They're always going to be a compromise between using the real protocol and using Matrix, but it does provide some level of connectivity between them. Now, the important things which are unique here is that no single party owns your conversations or your rooms here. So Matrix is very much a conversation history syncing protocol. It's not a messaging protocol. You're not going and just sending a message through like you do on email or a kind of, I don't know, a SIP message on Simple or indeed an XMPP stanza. Instead, you should think of it just like Git. In fact, you literally have a conversation history of your room, which is a Merkle DAG, so a signed directed acyclic graph of messages, just like you have inside Git. And that data structure is being replicated over all the servers which participate in the room. It's completely different to, say, XMPP or really any other chat protocol where you tend to have a centralized chat server. You have a whole bunch of users connecting to it, and that server just relays messages through. Instead, think of it just like having everybody with their own Git repository that represents the room, and they go and push messages to synchronize them back and forth between those servers. As a result, the conversations are shared between everybody. So digging in a bit more, if this guy on this server and this server here wants to send a message into a room which has people on that server and that server there, then they do an HTTP hit to this server. This will do 2 HTTP hits to the other servers, and the users on the other servers can do an HTTP GET. And typically, we use a long-lived GET request in order to just pull that JSON down. Let me show a quick animation to try to make this a bit more concrete. If we go to the matrix.org homepage right now, you have this little animation here that tries to spell out what's going on. So you've got the 3 servers. If Alice sends a message, it's literally a one-line HTTP post to a URL on her server. The servers then sign it, persist it into a graph of information. They then do a more elaborate HTTP hit out to the other servers, and at this point they've gone and signed the message with their signing key on this server. These servers go and persist it. Then you do a GET request from the other 2 in order to receive the message. So you're literally building up this replicated data structure across the 3 servers. Now, if Bob responds like this, they build up a graph. At this point, it's just a line. And imagine if Charlie races and also sends a message at this point. You end up with these 3 servers with different views of the room. But the nice thing is that it's an eventually consistent JSON database, effectively. And so as that message gets pushed out to the other servers, and indeed Charlie's message gets pushed out to the other servers, they end up coming in sync. So you get the idea. You're literally building up the same data structure across all the servers participating in a room. Now, practically speaking, if we jump into a matrix client like this one, this is Riot, one of the many clients out there, but this is probably the flagship that we build ourselves. And this room here has got, getting on for 7,000 people in it. As you can see, some of them have got ugly X and PPIDs. Some are on IRC, many are on Matrix. And in practice, this room is replicated over around 800 servers. So this guy, Freedom Lover, apparently is on Freenode. This guy, Matthias, is on his own personal Matrix server. This person is on Junta.pl, so another server. This guy is on matrix.org. So it's really going and bringing together people from Slack and IRC, different Matrix servers all over the place. On my personal account here, I'm in about 2,000 different conversations, ranging from everything from conferences to events to developer rooms to internal rooms. You can go and use these communities down the left-hand side to filter this down. So if I click that, it goes and filters it down only to our internal Matrix rooms, everything from VR to legal to end-to-end encryption to decentralized reputation work. Or I could filter it down even more and say, look at the people who support us on Patreon. And at this point, linear supporters is one of our Patreon levels. And we give them a room to talk about. You can shift-click on these in order to select more, at which point it expands up and you see the various different level of supporter rooms. Hopefully, you get the idea. Let me defilter that. In terms of the actual functionality you get in Matrix, you get things like read receipts. Slack still doesn't have read receipts. I have no idea why. And so if I say a message like, hello world here, then you'll probably see a couple of people going and bouncing read receipts down the right-hand side, assuming that the connectivity in the server is up to it. And I should warn you that the default matrix.org server is very loaded. We have about 100,000 concurrent users on it at the moment. And Matrix as a whole has got about 10 million addressable users on the network, so it doesn't always run as fast as it might on a big shared server like this. Hopefully somebody will read my boring message and you'll see some read receipts bubble down the right-hand side. Other things we can do whilst we wait for that is to say, look at all of the images. Oh, there's Amandine there waving, and you can see that Amandine, who's also sitting in the back there, has gone and got a read receipt down there. You can see people in this big room sending silly GIFs, showing off their keyboards, talking about particularly obscure red-black tree balancing algorithms, screenshots, more keyboards, it's a developer room, so it's all sort of people comparing their different apps and their different things they're working on in Matrix. So going back to the slides quickly. The Matrix ecosystem as a whole, the main thing that we deliver is this guy here, the Matrix spec, which is a big IETF RFC style document, which describes all of the APIs that you can implement against with client SDKs and backend SDKs. So you've got JavaScript, iOS, and Android. You have the bit which hits the SDK, the API at the SDK layer. Then you have UX, and then you have apps on top. There are third-party apps written by the wider community, and they're the green stuff which we provide as the project itself. On the server side, you have the Python implementation, a Go implementation, lots of bridges, and then the community has a whole bunch of servers and bots and bridges as well. A couple of interesting things probably to call out here is this guy, Riot X, where we've taken the old Riot Android app that was written in Java, and we've thrown it away. We did the thing that you should never do. We said, hey, we're going to write an entirely new app in Kotlin using the very latest best practices on Android. I think they call it the Jetpack kind of set of libraries that Android recommends when you're working on the latest features. And this is really exciting. It's really a completely new app. And before I get into the fun low bandwidth stuff, I thought I might give you a sneak preview because it isn't in the App Store yet, but it's worth taking a quick look at. And that's a good start in terms of my screen share. Let me try to get the screen share working again quickly. Don't know why I bother. It always works a minute beforehand. No devices found, but you are plugged in. 1 second. There we go. So this is my old Galaxy S6, I think, possibly an S5. Oh no! Sorry, let me kill PowerPoint from doing its horrible thing. On the plus side, you didn't see that it all crashed. So here is Riot X running on Android. And I'm scrolling through my thousands and thousands of rooms there. You can see even on the screen share from my phone, it's really quite smooth. We've simplified things down to have 3 different tabs here. You've got the rooms you're in, you've got your ongoing conversations, you've got the home screen, which is a new one. You can see James there in the front saying, hello, ComCon, in a DM to me in the direct messages there. And in fact, the home screen now shows you the rooms you need to catch up on. I've got 96 places where people have messaged me since I last caught up, which gives you an idea of how active my Matrix account is at least. You've got James plugging us on, say, the VUC IRC channel. Ooh, you've got internal rooms, you've got customer rooms going on. Obviously, you have people in the office trying to arrange lunch because that's, well, everybody in the office spends their life worrying about it 11:15, and so on. So really, really fun app. And if we actually go into one of these rooms, I'll go in and say hi to James here and say hello. We can also demonstrate some of the latest stuff we put in here. For instance, we now have reactions. It's surprisingly hard to do on a decentralized system because it's easy to get lots and lots of reactions stack up, and you have to aggregate them and replicate them in a relatively secure manner between the servers so that people can't lie about who reacted to what. And I can go and send James a reaction like this, and yes, it does work. We can also edit messages, so if I go in here now and hit the edit button, hopefully, come on you. Whoop. Oh, this is very meta. I hope you're enjoying a demo of a demo. I can go and change the hello to say, hello, James, and hit send, and now, hopefully, the hello message here will say, hello, James, edited. I can even click on the edit button here, and I haven't actually tried this. Oh, there goes the app. So there's a reason it hasn't quite made it to the App Store yet. But basically, entirely new Matrix app that should be at least as good as Telegram or Slack in terms of the usability. So low bandwidth stuff. Let's talk about the good stuff. We had a mission to get Matrix down to 100 bits a second. So we talked about this at FOSDEM. Was anybody at the talk at FOSDEM? James. Okay, brilliant. Everybody else can hear this for the first time because there's quite a lot of there's a lot of material that's been reused here. Our target here was 100 bits a second, and just to put things in context, the way to think of 100 bits a second is that it takes 2 minutes to send an Ethernet packet at 100 bits a second. So 1500 MTU, we're literally talking about like 180 seconds, 200 seconds, or something like that. So why would you ever want to do this? And we can't talk about the specifics of the use case here, although I'm sure that you might be able to extrapolate a bit. But basically, there are scenarios where connectivity can get really bad, like particularly in life or death situations. And in fact, something that we can talk about is that the US Department of Public Safety have been using Matrix for hurricane relief. And in a situation where you might have people stranded, drifting in and out of GSM connectivity, you want every single bit to count. And you do not want to have things timing out after a few minutes and think, oh, well, I never got my SOS through. And let's face it, an SOS is what, a byte, because the crappy network protocol needed kilobytes and kilobytes of overhead. So we started off looking into this with obviously what Matrix does today. And we built Matrix to be really pragmatic. It's not in any way, by default, bandwidth efficient. It is just HTTP 1 on TLS. And we use JSON for a transport. It makes it trivial for anybody to send a message. It's literally a curl one-liner like this. Let me zoom it a bit. And we went and benchmarked to see how that looks. And it's about 7,000 bytes, including the Ethernet headers. And to do a TLS 1.2 handshake, as well as set that up from scratch, it's about 8 round trips. So in practice, that means we've got about 10 minutes to send a message at 100 bits a second. I think we all agree that 10 minutes to send a message probably sucks, especially if it's like 1 byte. Obviously, it could be so much more. Now, obvious thing we can do on top of this is to just switch to HTTP2. Literally, for curl, you add --HTTP2 to curl. And, well, the good news is we get some header compression going on. It's a bit more compact. You have binary headers. And we've saved a whole 300 bytes there. Now, a lot of that is the TLS certificate overhead, but a lot of it is just the sheer overhead of HTTP as a whole and JSON. Now, the next obvious thing to do would be HTTP 3, which I'm sure you know that HTTP 3 is actually HTTP-led over the quick transport. So it's no longer TCP. We're doing it over UDP, over the quick transport that Google and others have been working on for a while. And we're now using TLS 1.3, which is nice because we can reuse certificate handshakes across concurrent requests, even if they're not part of the, it's not TCP, so they're obviously not in the same TCP stream, but you do still have to do a certificate handshake at some point. It's good because I think you get, you can do 0 round trip setup if you already have SSL context. You can do 1 round trip setup if you are setting up from scratch. However, you still need to do 6 in total, empirically. And interestingly, it's not that much better for bandwidth. So by default, you're getting 6,700 bytes to send the same message. And one of the big reasons for this is that Quick mandates in the IETF RFC that you have to bit stuff the setup. And the reason for this is apparently to mitigate amplification attacks, that you don't want to make it too easy for people to abuse UDP relaying systems to go and build up echoes which get bigger and bigger and bigger, whereas if you start off close to the MTU, perversely, apparently, it makes these attacks a lot less. Once it's established, it's 900 bytes to do the next request, so that's an improvement, but it's still very much not ideal. So we decided to go in a completely different direction, which is a bit risky, honestly, given that Quick is very popular. You've got all of Google, a lot of IETF people pushing it. And we went and looked at CoAP. Has anybody actually played with CoAP? Okay, CoAP is an interesting protocol. It's about 4 years old, 5 years old now, and it's RFC 7252. Cisco pushed a lot of CoAP development, and it is a RPC protocol specifically for IoT. So it runs over UDP, but everything is designed around bit efficiency. In fact, it's almost 2-bit efficient for what we're doing. For instance, they assume that every request should fit inside a single packet. So their default is 1 round trip. They believe that if you're doing an RPC request over CoAP, 1 packet for the request, 1 packet for the response, and you're done. They consider like reliable transmission to be very much a kind of optional overhead, and the idea of splitting a packet, splitting a request into multiple packets is really quite sophisticated. And the good news is, therefore, it's one round trip. It also maps almost directly to HTTP. Now, it's not HTTP, but it feels and smells a lot like it. You have GET, you have PUT, you can use, you have URLs, you have query strings, you have payloads on your PUT, and you have bodies on your request, you have content types. It feels like HTTP, but it doesn't attempt to be actually compatible. So now, perhaps we're getting somewhere. 500 bytes, 40 seconds to send a message. 40 seconds is starting to be doable. Problem is that CoAP, of course, doesn't give you any encryption by default. However, it does suggest that there is a recommendation using DTLS, which is TLS over UDP, using private shared keys. So rather than a certificate authority with all of the bulk of putting X509 certificates around the place, instead you can literally specify some kind of static shared key and then use that to go and authenticate and encrypt either side of the conversation. And there is a really interesting IETF draft by this chap, Matson, who goes and compares all of the overheads here. And at this point, we can be getting as low as 15 bytes of TLS overhead per request, as opposed to 900 for Quick or like 7,000 for HTTP 1 and 2. Problem is, though, that very few CoAP stacks support DTLS, especially in Go. Since I originally wrote this back in February, there's been some more progress on one of the Go CoAP stacks to do it. However, and also private shared keys are a hassle. It's literally, you need to out-of-band go and configure up the secret for both people, and that doesn't give you any of the flexibility of a certificate system. So we decided not to do DTLS. There's also another kind of security framework for CoAP that we could have used, which we didn't, honestly, because we didn't really know about it at the time. And instead, we decided to use noise. Anybody know about noise? Someone? Anyone? Noise is great. Noise is noiseframework.org, and it's a meta protocol for building cryptography transports, basically, or cryptography protocols. It's written by Trevor Perrin, who's famous as co-creating the double ratchet algorithm that Signal uses. So he works alongside the Signal Foundation on Signal. And Noise was created, I think, both for use in Signal. In practice, it's also used by WhatsApp, so it's pretty wide deployment. And a whole bunch of more interesting use cases. Facebook just rolled it out in Libra, their cryptocurrency solution, as a very, very lightweight cryptography protocol. Now, the problem is that Noise gives you building blocks to build a transport. So you can use it to build transport layer security of some flavor, but it's very much saying, hey, what handshakes do you want to use to get the right security semantics? So we're slightly in build your own crypto territory here, which everybody should know is a very, very bad idea. Defensively, though, to try to optimize for bandwidth, we don't really have much choice. So we decided to use what they call the noise pipe pattern, which is a combination of two different handshakes. And the way noise works is that you get elliptic curve key pairs, and it defines semantics for doing Diffie-Hellman-based elliptic curve Diffie-Hellman key exchange. So for XX is how you would start a handshake to establish a secret key between two endpoints. You start off sending a ephemeral key over, and these guys are 32 bytes per token, roughly. And then the other guy will send back their ephemeral key, as well as various other tokens that you combine in order to eventually negotiate a shared secret S, which it comes up with and is confirmed on this side. So by this point, you've basically done one handshake back and forth before you can start to send encrypted payloads, encrypted using a secret that you have securely authenticated with one another. And then there is an IK handshake, which means that if you have established that secret, you can re-establish it with 0 round trips. So you can go and re-establish after a big hiatus an entirely new session with a new secret, completely with the payload in there. I think I've mangled that a bit, but basically it's the idea that the overhead for establishing an entire crypto context, we're talking like 96 bytes, as opposed to the 900 or the 7,000 we were getting in TLS. And then it's about 16 bytes per message after that point in order to have the authentication tag. So that's the transport layer of what we did. On the payload itself, obviously JSON sucks. No, it's 35 bytes for a message like that. Some easy thing we can do is to switch for CBOR, which is the binary encoding that CoAP typically is paired with. This gets us down to 26 bytes, so it's only a 25% improvement, but it's relatively concrete. However, a lot of that space is taken up with horrible ASCII or UTF-8, like message type and m.text and body and test. So the next obvious thing we can do is to really improve the payload. In some places, we can map bulky HTTP URIs down to a numeric root ID for CoAP. So it takes like 50 bytes URL down to 1 byte. However, doing that manually gets a bit boring, and we ended up doing a slightly nasty hack, which is to use the deflate library in Go. And deflate is basically an LZ compression system or a deflate compression system. And what you can do is to train it on a dictionary of the most common things. So going back to this, m.text and message type and body are all very, very common. So they're going to be compressed down to like a couple of bits, typically. And then you run everything through that with a pre-shared dictionary. And it works very nicely in that it gets the entire request down to 90 bytes, including all headers, including Ethernet headers, and then 16 bytes to the crypto overhead if you need crypto. Now, at this point, we're talking 8 seconds to send a message at 100 bits a second. I should say this is horrible from a protocol perspective. Imagine if you published an RFC that said, in order to get the bandwidth down, all you need to do is to load up this hard-coded pre-shared dictionary to compress everything. But from a pragmatic perspective, it's really getting interesting. And at 8 seconds, I think that's genuinely usable, and we basically considered ourselves to hit the target. So what this actually looks like in practice is that you have matrix clients like Riot and RiotX that we were just looking at, and normally they would talk straight to a server by HTTP. Instead, we wrote a Go CoAP proxy that bluntly takes the HTTP, and it's like 7 kilobyte requests of JSON, HTTPS, TCP, IP, and Ethernet, squidges it into this totally different stack, but it's basically a one-to-one mapping between HTTP and CoAP. And here you end up with 50 bytes for the CBOR CoAP inflate layer, 16 bytes for noise encryption, 8 bytes of UDP, 20 bytes of IP, and 14 bytes of Ethernet, assuming IPv4. And it's coming up at about 100 bytes in total, depending on the message size itself. So that is a 65 times improvement over HTTP. Now, it obviously has some problems in that things like retry support needs to be implemented effectively at the application level because we don't get reliability on UDP. We also have to do some really interesting things to avoid doubling up basically the framing of the transport. Because by default, the framing would happen at the CoAP level, but if that is both compressed and encrypted, you need to have the framing instead at the next level up, so you can handle retries and working out badness there. And so we go and solve that by hoisting the headers from CoAP, not encrypting them, and putting them outside the encrypted layer. So we only have one set of headers, but we deliberately sacrifice the encryption of the metadata in terms of like the sequence number and the session ID and that sort of thing, rather than having it buried in the encryption. We did that manually. In practice, there is a spec for doing it, and we should have used that in retrospect. Enough talking about this. Shall we actually see what it looks like? So in order to build this, we needed a nice network simulator, and I apologize if anybody came into this hoping to see this happening with hardware. I was wanting to demo it on real devices and like have a Raspberry Pi and we throw one out into the field and have a horrible connection and see how well it works. In practice, sorry, I haven't had time to do it, so we're going to do it with virtual hardware instead. And we have this thing called meshsim, which is an open source project you can find on GitHub, matrix.org, meshsim right now. I'll fire it up. And what it does is to give basically orchestrate Docker to fire up lots and lots of matrix servers in a network topology of any kind you like. It provides a web interface, which looks like this. And can everybody see okay? Is that coming through? Basically, if I start clicking here and spinning up servers, then literally you can see in the background we have both Docker spinning up, creating synapses, and then using an awful lot of TC, QDisk, and TC filtering to create a network of precisely the topology that you draw. And you can edit this thing in real time, move the servers around. Let's have a nice big network with, I don't know, 15 servers, say. Wait for Docker to do its thing. You can see my poor Mac desperately virtualizing away, spinning up all these Dockers. Come on, you can do it. Yay, there we go. It's a nice complicated mesh network, nice complicated topology. You can see the latency between the nodes depends on how far they are. So this is 100 mils there, but if I change it up, it's now 129 mils. We go and put a threshold on how close they have to be in order to talk to one another. And literally, I can go and log into one of these servers. So here, oh, no, that's not right. Where's one of my rights? Yeah, too many browsers. Okay, so here I am logging into this one here is Synapse Naught on right. And to quickly get a test network up and running, I'm going to run a few scripts. First of all, where am I? First of all, I'm going to make a room on Synapse Naught. Let me zoom in so you can see. And then I'm going to tell everybody to join that room. So I'm going to create a user on all of these 15 servers and tell it to join the same room. Like so. And you can see the JSON request coming back. And what we do is to visualize the actual HTTP hits going through the network in real time. So the mesh simulator is going and phoning home to the web interface by a WebSocket, and every time the Synapse sends a message or receives a message, it's going in like so. And it's literally going through, so 12, 10, 13 should be next, probably. Oh no, that was 12, then 13 will be next. 14, 15, something like that. Basically, all the servers, hopefully, are now in the room. Now what I can do is to send a message from this one. Now let me go and shrink down. Let me get rid of that so you can see what's going on. And I'm going to do a typical message today, which looks like that. You saw it going from 0, going out to the others, coloring them in with the ID of the message that is being sent. That was pretty fast, so let me slow down time. It is Matrix after all, and go and change latency to that, and scale everything to go 5 times slower. And if you look at the graph, you'll see suddenly our latencies are up massively here. And in fact, if I go and log into one of these servers quickly, just to show this is a real demo, I can go, well, docker exec, -IT, synapse naught, say, and open up bash there. So I'm now shelled into that server, and I can trace route through to synapse 15. And you can see, well, weirdly enough, it's going to take multiple seconds to get through the network, and I didn't give traceroute a high enough timeout, but it got as far as 11 before it timed out. So that's going 0 to 1 to 5 to 6 to 11. It's clearly just going over the top of the graph. So, it's a real network going on there. And if I now send a message through, you can see that we're doing a full mesh fan out of messages across the mesh. Now, as it happens, it's doing CoAP, and we, how shall I best show this? Well, first of all, let me also demonstrate that we are experimenting with better than full mesh routing. So if I send a message now like this, you can see there are relatively few messages propagating through the network, because previously we sent 15 simultaneous requests from 0 that went out to the other servers, whereas here we got the same coverage. It was about 40% slower overall, but there was typically only ever one message sent from the server. So it's not actually creating a spanning tree over this mesh. Instead, it is doing some really funky routing, experimental routing stuff, where it basically partitions the network based on what it can see locally, a bit like OSLR or OSPA. Well, yeah, OSLR is the closest routing protocol to this. And then it goes and strategically sends out as few as possible. There's a bit of overlap, but in the end, you can see it's getting coverage with minimal global network coverage. Now, what else can I show you here? Let's actually look at the network, I guess. Let's go and, well, I'm shelled into this guy here. So let's TCP dump. I've totally forgotten what interfaces I have here. Let's TCP dump F0, which has got that alias. So TCP dump, E0, How should we do this? Lots of V's, probably some XX as well. Uh-oh, it's got a terrible busy box one. Let's just do it without that. Okay, so we've got a TCP dump running there, and let's go and send another message through. And if we look at the sort of sizes, the problem is that we're getting the database traffic on here as well as the UDP and the CoAP stuff. Let me filter it down to just being the CoAP. I think that is just, how much port are we looking for? Where's our UDP gone? In fact, it's probably the only UDP traffic here. So let's try that again. There we go. So this is more no, that's DNS. We don't care about DNS. Sorry. No, not port domain. Can you see this is the bit that I forgot to practice? So let's try again now. Oh, all right. Oh dear, we still get it. All right, I think that one there is a legitimate UDP one on port 5683, which is the CoAP port. So I just filter it down to UDP port 5683. Try it again. Right, there we go. So here there is a typical one of these CoAP requests. This particular one is 93 bytes. The one afterwards is 213. It's probably got, and the reason for that, and this is really cool, who knows Jager and open tracing? No? Jager's amazing. So Jager is this lovely thing created by Uber, which allows you to build sequence diagrams across massive systems. And I actually have all of these synapses phoning home, as well as to the web visualization into Jager. So if I say pick, synapse naught here, and I query all of the traces, it gives me this kind of heat map of stuff going on. And if I click on it, you get a sequence diagram of all of these messages going through. And the reason it's a bit bigger is that it's sending the metadata through to Jager so that you can see this went from 0 to 1 to 10, and I think it lets me do that. There we go, to 13, to 12, and you can literally plot one by one. If we go and click into one of these, we can look at a particular CoAP or HTTP request and dig all the way into it to see precisely what was going on, particularly around the routing. I'm starting to run out of time and breath here, but hopefully this gives you an idea of how cool this could be. And it's all open source. The funky routing stuff isn't open source yet, unfortunately, but this test jig is. So if you have a mesh network which you want to visualize and play with, it has some good support for doing that sort of thing. And I think I'm probably over time, so I should probably shut up.
Cool.
Thank you, everybody.
Thank you. So we got 2 minutes. Fortunately, the next speaker is me, and it's going to take me a second. So if you want to carry on and do a couple of questions.
Okay. James.
Yeah, very quick one. How does this cope with constantly changing network conditions?
It does it well. I mean, so for the funky routing, which is really the only point that it cares about, I mean, if you've got lots of loss, then obviously that's handled by retries. The point of having this dynamic thing is that you can literally go and rewire it, obviously, like that. And so it's easy to play around to see how things change with latencies. For the funky routing algorithm, what we call the fan-out routing, it needs to know at least the local network latencies. And if they are keeping on changing, you do need to have some kind of metadata on a routing protocol to tell you what the latencies are. At the moment, we cheat because we know what they are, because we're drawing them on this graph, and so we basically steal our God's view of the world in order to know the most efficient routing paths. But if you had an existing IP-level routing protocol like OSLR or Batman or other ones like that in there, then we could use that instead. So in practice, yeah, it should work pretty well.
Brilliant. Any other? Michael?
Within the fanning tree, I noticed that it hit some of the nodes more than once, and it's visible because the latency's so high. But in the real world, is there a probability of almost like a network storm, or is it?
So first of all, it isn't actually a spanning tree. Instead, what it's doing is tracking a bit mask of the servers that it's already been to. So basically, every time, it's more like a mouse finding its way around a maze kind of algorithm, and you dump mice into different bits of the maze. However, In general, it doesn't actually overlap the same servers. So if I send another message like this, and we look carefully, sure, everything is going to go through 1 because that's the physical route. There's no other wire connecting 0 to anything else but 1. It does send multiple packets out just because it's more efficient to kind of have multiple branches to the tree. It's not a binary spanning tree, it's literally doing multiple paths. But it shouldn't be, typically for a typical mesh, it shouldn't be too much overlapping. I realized very quickly there's one final thing I totally forgot to show you, which is very fun, which is obviously, if you send them all sending messages at the same time, it lights up like a Christmas tree, which is very, very fun.
Thank you.
Thank you very much, everyone.
Yeah, our mic for Sam. Sam is a man who probably needs very little introduction, a renowned abuser of communication systems, and today he's going to focus